Okay, so we're about to start an entire unit on the normal curve, which is that like bell-shaped curve that we use to analyze all sorts of things that have central tendency. Normal curve belongs to a larger family of things that are called continuous probability distributions. Okay, so the problem with a continuous probability distribution is it's very similar to the discrete probability distributions that we've been working with, like the binomial distribution and the Poisson distribution, in that you have a random variable x. Like when we did the binomial distribution, x represented the number of successful trials out of n trials. When we did Poisson, x represented the number of occurrences over a given interval. And we had some way to go from x to the probability of x, which is the probability that that number of trials occurred, or the probability of that number of occurrences occurring over a given interval. But in all of these, the values for x had to be countable. Okay, so like you had either 0, 1, 2, 3 successful trials, or you had 0, 1, 2, 3, 4 occurrences. They had to be countable. It could be an infinite number of them, but it had to be countable. When I have continuous, I am non-countable. Okay, so this means that over a particular range, I can have, there's no gaps, there's no overlaps, but each number is actually there. So like if I do height, you can be 5'1.5", you can be 5'1 3/4", you can be 5'2 7/8. So these are non-countable realities. You can be any height in between those two things, so that between any two given heights, there's an infinite number of possible heights. So the problem here is when I did this with discrete, like binomial or Poisson, I could build a table, right? I could put x here, and I could put p of x here, and I could write 0, 1, 2, and then get p of x values, because I could count these. But now if I had like x as possible heights, this doesn't make sense anymore. So what we do is we create something that is called a probability density function, and we'll take a look at how those work. Okay, so a probability density function is some equation that when you put in values, you get back a curve that will allow you to calculate the probability distribution for a continuous function. So let's give an example here of something that's a possible probability density function and see how it works. So let's say I have the probability density function f of x is equal to x, sorry, not x, e to the negative x. Okay, it's a pretty simple function. If I were to graph this thing, it looks like this. I start up here at 1, and then maybe this will be a half, and then 1, and then 3 halves, and then 2, and then 5 halves. And what this function does is it kind of comes along here, and it just keeps going, and it gets closer and closer and closer to 0. So I'm going to put this function on the domain where 0 is the lowest possible x value, and it goes off to infinity. Okay. So this is a little bit different than a probability distribution function. Like if I had a probability distribution function, I want to know the probability that, like something could be 1. I would just like graph this and go, oh, what's the height there? And that's 1. But see, here, the probability of a continuous random variable actually being 1 is 0. It just can't be. It's just like saying nobody is exactly like 5'9". They're always 5'9" and either a little bit less or a little bit more, but it doesn't make sense to say, like, if I picked a person at random and said, are you exactly 5'9", the answer would be no. The probability is 0. Okay, so like let's like make this say X is number of hours since last meal. All right, so how long has it been since the last time you had a meal? All right, so this might actually give me that probability density. Okay, so let's try to figure this out. Like, what is the probability that a person selected at random the last time that they ate was within the past hour? Okay. So what does this mean? So the way a probability density function says is that this means that I want the probability that X is between 0 and 1, right? What's the probability that they have eaten within the last hour? And what it is it's not so much you're not measuring countable data, but that area, if you calculate that area under the curve, it gives you the probability that the person has eaten within the past hour. Okay, so this is like area under a curve stuff. All right, so my argument here is that this is going to work. Now, here's the thing. In this course, you will never have to calculate that area by hand. No. Why not? Because the method that you use for doing that is in a course that is not a prerequisite for this, and it's called calculus. Okay? So calculus, the second part of calculus is all about calculating area under a curve. So we're not going to make you do that. And in fact, when we get to the normal curve, you'll see that your calculator has built into it this method for calculating those curves. Now, just out of curiosity, like if this is my probability density function, right? What is the actual probability that somebody has been like within an hour of their last meal? Now, granted, this is just like completely fictional and made up, but if this were the probability density function, what would be my answer? Well, I'm actually going to go to my calculator and have it calculate that for me. All right, so here we go. We're going to actually put that probability density function in here. I'll put it in Y1. Now, you will never have to do this particular thing in my course, okay? But I'm just kind of doing some exploration here so you can see what's going on. So there's that in Y1, and I'm going to window my calculator so it kind of looks like what I had on the scratch work. So my minimum X would have been 0, my maximum X would have been around like 4, my minimum Y was 0, and my maximum Y was like 1, and I graph it, and there's the curve that I was talking about, right? So what we want is like, so this is probably 0 to 1 here, right? Because that's 1, 2, 3, 4. So I want the probability that I'm in this region, right? So I shade like in there, below the curve, between 0 and 1. Well, what's nice here is that the calculator will actually do this, okay? So if I go to math, this is where the calculus-ish stuff comes in. You get a integral, and we're going to go from 0 to 1. Yep, don't worry about the math here, just stick with me. I'm going to go to vars, and say do this on y1, which is where I stored that function, and say x, and I hit enter, and it returns, boom, there's my probability. 63.2% that if I picked a person at random, that their last meal would have been between 0 and 1 hours. Okay, so what about like, what if it's been like 3 to 5 hours since their last meal? Well, I do that same integral. I just put in different bounds, right? So it's like, this is the area between the 3 and the 5. And if I pick a person at random, the probability that their last meal has been between 3 and 5 hours ago would be about 4.3%. Okay, so wait a minute. Okay, so let's say, what's the probability that they've eaten within the past 20 hours, right? So, or like in the past day, let's go to 24 hours. 0 to 24 hours, right? And this gives me 1. Okay, so is that really 1? All right, so it's probably not, right? Like, it's rounding to 1, right? So, like, but it's a pretty good idea here. Now, here's something to note. No matter how big I make that upper bound, this thing, like, let's make it 999, this thing is always going to round to, wait for it, 1. Because what it's saying here is that as I look at that curve, as I go out to infinity, there's very little of this curve that's left, right? So my calculator is literally rounding that area to be 1. But it's never going to get bigger than 1 because the total probability of an event occurring can't be bigger than 1. This is what makes this a probability distribution function or a probability density function, is that the area under the curve has to be exactly 1 on its domain. So this is why this is a good choice. All right, so we're going to look through like some things like uniform distribution, and the area under the curve will be 1. And then we'll look through something like the bell curve, which is a little more complex. And the area underneath that curve will also be 1. Okay, so we'll take a look and see how that plays out. Just to kind of give you an idea of what I'm talking about here, let's see that with the bell curve. Okay, so I'm going to do something a little bit weird here. I'm going to put in second distribution, second vars, and I'm going to take the normal PDF, right? And I'm going to have x be the x value with a mean of 0 and a standard deviation of 1. You have no idea what this means at this point. And I'm going to window from like -3 to 3, and we're going to have y min and y max at 0.5. And we're going to graph that. All right, so boom, there's my bell curve coming in on the screen. So now with the bell curve, my values can go from like -infinity to infinity. So let's see what happens here. If I go back to my main screen, right, so second quit, and I bring up that integral, but now the bell curve's in this integral, right? So if I go from like -99 to 99, right? And I calculate that. This comes out as, taking a minute. It needs to think 1. How about that? So we're saying that the area underneath that bell curve as I go way out to the far tails is actually going to be 1. Now, let's try something here. If I go from -1 to 1, we should be able to anticipate the answer here, because this is going from between the first standard deviation and the bell curve, which lo and behold comes up as 68%. Wait a second. In the bell curve, the distance between the two standard deviations is 68%, right? 1 standard deviation out, because that was the empirical rule. If I do 2 standard deviations, remember this said I was supposed to come out with 95. And there it is, 95%. So we'll look a little bit deeper at this as we move forward into continuous probability distributions. But this is just kind of getting you started on it. There's no immediate homework attached to this. It's just a matter of getting you familiar with the thinking in this section.